Hello, a great welcome to Idea Statica tutorial. Myself is Jarajan P. This is tutorial number 25. In this tutorial, we consider a standard column beam moment connection that is provided with the slip critical boards. The various components of this connection are verified using the provisions laid down in AISC-LRFD-2016. So let us start Idea Statica tutorial number 25. Please note that the link for the playlist for all previous tutorials is given under the description of the video. So the model used for the given tutorial is shown here. As you can see that it represents a simple column to beam moment connection. The moment connection is developed using the arrangement of the top and bottom plates, and in this tutorial the top and bottom plates these are connected to the beam flanges using the slip critical boards. And as you can see that these top and bottom plates, they are connected to the column flange using the full strength butt weld, and the beam web, it is connected to the column flange using the double-sided ankle through the normal A307 bolts. So let me quickly introduce you to the components of the model. So as you can see that the column, it consists of a W360 by 179 section, and the gamma angle is kept as 90 degrees. And here as you can see that the material for the column, it is kept as A572 grade 50. Now going to the beam, you can say that the beam cross section is W530 by 92, and the same material, that is A532 grade 50, is used for the beam material as well. And as you can see that the geometrical type is NZ1, and here what is done is that the forces applied on the beam, they are assumed to be at the column face. Accordingly, the forces is specified through a position given by x is equal to 185 mm. So that is all about the column and the beam components. And now the balance components of the connection, such as the top and the bottom plate, angle plates, all these are being developed using the manufacturing operations. So let me quickly take you through the TFPL, that is the manufacturing operation that is we have used for the generation of the top plate and the bottom plate. So as you can see here, the top flange plate, these two plates, that's the top as well as the bottom plates, these are generated through the fin plate manufacturing operation. So I can just show you where the fin is. So here you can say that it is somewhere here. Yes, so this is the fin plate manufacturing operation that is used to develop the top and the bottom plates. So as you can see that here, for example, considering the top flange plate, the member on which it is provided is a B, and is connected to the top flange of the beam B. And please be very careful regarding the materials. The top flange plate, it is a A913 grade 50 material. The thickness is kept as a 18 mm, and the connection type is taken as a bolted. And this is also a very important parameter. There is an overlap of 400 mm between the plate as well as the beam flange. And then we have the bolts, and here is very important to specify the bolts. So in fact, Idea Statica provides both the NPTEL as well as the metric system of specifying the bolts. Here as you can see that it is specified as a 24 mm A35 bolts. M indicates it is being the metric system we have followed, and the position of the bolts are already specified here. And this is very important. That's a shear force. Idea Statica provides us two modes of a transfer of the shear forces. That is one through the bearing tension or shear interaction, and the second one is the friction. And here, as I told you, we are using the slip critical boards to connect the top and the bottom plates to the beam flanges. So accordingly, please select the friction. Now regarding the welds, here what is done is that both the top and the bottom plates will be connected to the column flange through a full strength butt weld. So accordingly, this weld is chosen here. That's a butt weld. Okay, so accordingly, we need not to specify the size of the weld as well. Now here the thing, one very important thing is that as far as the top plate is concerned, we are connecting to the top flange 1. Okay, now In a similar way, we can also generate the so-called the bottom flange, and only difference is that instead of the top flange, we have to specify it as the bottom flange, and all other parameters will remain the same. And here you can see that 24A325M bolts are being used, and it is being friction, right? Now, finally, we have got to specify one of the cleat angle operation, that is here it is given here, and this is being done through the cleat operation, as you can see. So this cleat is already provided here in the manufacturing operation. So you can specify the various parameters required for the development of this cleat member. So you can just zoom it a little bit. So you can see that here it is. Yeah, so this is the angle member. You can see that this is the angle that is provided on both sides of the web, and it is essentially as you can see that a it is of a size. You can see that it is you can just edit it and see the size. It is a angle of size 102 by 102 by, and the thickness is of 8 mm, and we have specified A913 grade 50 as the material specification for the angle. And here please see the specification of the bolts as well. That is very important. Here we have used 5 by 8. 5 by 8, it is in the imperial system, 5 by 8 inch. That is the diameter of the bolt. And A307 is the different quality of the bolt, because to connect the column, the beam web to the column flange, we don't go high strength bolts. So A307 bolt is specified in this case, depending upon the magnitude of the forces. And here one very important thing is that these bolts which connects the column, that is a clip angle, or we call it as a cleat angle, to the beam web as well as the column flange. This is essentially a normal bolt. Okay, so accordingly we have chosen bearing tension shear interaction. It is not a friction grip bolt, or it is not a critical bolts. Okay, so finally let me introduce you to the load effects. So we have the load effects, and here you can see that the beam end, it is loaded by a shear of 400 kilonewton. So here we can see that there is a vertical shear of 400 kilonewton, and then it is an applied load of say 300 kilonewton meter. So let us quickly calculate the model just to see the position of the various components. And here it is very important that we inspect the results of the various components thoroughly, and ensure that yes, the joint has behaved in the way we want it. Okay, and one very important thing I want to tell you is that before the verification of the results, the design engineers need to read the various relevant provisions to the AIC, and just see where Idea Statica has taken the reference values, so that we know that how the capacities, the design strengths of the various components like the plates, bolts, and the preloaded bolts are arrived at. So yes, the analysis has run. So we find that it is 100% run, and with the plates we find a little bit excessive strain 0.6. Okay, there's less than 5%. And the bolts here, as you can see that there are two types of bolts specified. Bolts means it's a normal bolt. Normal bolt means, as we have already discussed, normal bolts are used for connecting the cleat angle to the beam web as well as to the column flange. And then here we have got preloaded bolts, which are known as the slip critical bolts, right? And we know that here the connection of the plates with the beam flanges are done using the slip critical bolts. And please remember that normally in the field, based on my experience, normally we go for the two types. One is a snug tight, okay, and whenever we use the slip critical bolts, what is very important in the site is that you must be able to monitor what we call as the torque applied on the bolt. And nowadays we have got various advanced even corrugated washers, just to see that only the required pretension is applied on the bolts. And then there are again various methods that people use, for example the torque wrench. Then there is a nut out of turn methods. Many techniques are available in the field in order to monitor what we call as the applied pretension in the slip critical bolts, because the performance of the slip critical bolts depends upon the pretension that is already imparted to them, right? That is one thing. And another thing is that here in the case of the slip critical boards, as we know that the friction, the resistance to the shear, it is generated through the friction that exists, okay, between the contact surfaces. So here through the pretension, what we do is that different contact surfaces are held tight, right? So that based on the pretension, we have got a shear force which is nothing but mu into the pretension, right? This is a simple fundamental of the slip critical boards. So let us straight away go for the verification of the components. So we have to go for the check, and in the check you can see that here, yes, analysis. Let us quickly see the analysis. Yes, it is done for 100% of the loads. Now coming to the plates, let us quickly go for the plastic strain before going to it. Yes, if we find that the plastic strain, let us just arrange the values in the order. So the 0.6 percentage, it is coming in a, yes, it is coming in the bottom flange plate, and the top flange plate, it is a 0.4 percentage. So what we find is that as far as the plate strains are concerned, the top plate and the bottom plate are the critical components, and we find that there is some kind of a strain accumulation here also in the column web, the beam web. Yes, that's what is being written here, this 0.3 percentage, right? So let us quickly see how exactly is the strain distribution in the various components. So what I can do is that let me just increase this a little bit area so that we can see it a little bit clearer. So you can see that yes, this is the distribution of the strain. You can see that at the zones very near to the its connection to the column flange, you find that there is a concentration of the strains, and these strains have gone up to say 0.6 percentage. Now the same is the true case for you can say that if we select the other plate also, that is the bottom plate, you can see that the strains here, there is a red color indicating that it has gone up to say 0.6 percentage. All right. Now on the other hand, if we take for example the beam web, yes, in the beam web as indicated here, we find that yes, there is some kind of a concentration of the strains near the column web portion. So this is all about the distribution of the strains. So now let me quickly take you through the equivalent stress. That is also very important to us, because see, the equivalent stress is a very important thing, because we need to check the various components also. Look here. So if you see the distribution, let me just quickly take this one. Look here, there's the distribution of the equivalent stresses in the top plate. So we find that has gone up to say 300. So it is almost, it has utilized its capacity, which is 300, right? And that means the stress we have seen the strain is also concentrated here accordingly. Obviously, the stress should also be concentrated in and around, or it's near its connection point to the column flange. And you can see that the stress distribution in the plate, it decreases okay, with respect to its distance from the column connection, right? And let us also quickly see the stress distribution in the column flange, obviously in the column web. So the column web also in the beam web, sorry. So here you find that we got only a minimum stresses of the order of say 75 Newton per mm square in the connector zone, but near the column, near the bottom web portion, could be this is due to the compression that is developed in the zone. Okay, we have got stresses that is going up to say 275 levels. Okay, now one very important component that needs investigation is obviously is your the web panel. So this portion is a very important portion, right? And in many cases what happens is that we find that due to the large concentrated forces that is transferred through the connection, we find that there is a lot of stress concentration. Look here, so you can see it better here. So this point, it is mapped to this one. So you'll find that yes, there is a stress concentration. The stresses are going up even up to the tune of say 200 to 225 in the column web. So in cases where the design engineer is interested in keeping the stresses in the column web below, that is to avoid the so-called the buckling criteria, what he can do is that he can add the additional stiffness. So that obviously the addition of the stiffness will drastically bring down the stress distribution in the column web. Okay, so that is all about the plastic stress distribution or the equivalent stress distribution. Now let me quickly take you to the boards. And here the boards, I mean, it is nothing but it is a normal boards that is used for connecting the cleat angle to the beam as well as the column. And here let me just see what's the ratio. Yes, the ratio is very small. So let me just quickly arrange it. It's only 33.9. So this is 33.9 boards. And it is important that the engineers just double click this and see that whether what happens is that when you start checking the results, you will you are indirectly tracking whether you committed any kind of a mistake in the material specification or in other minor mistakes. So please press it, and at the same time please match all this expression one to one with the AIC code. Now look here, so it has performed. So please remember that the chapter J of AIC 36016 is focused only on connections. So you will find that J in front of almost all the checks, right? So tension resistance, it is checked for this bolt. As you can see that it is used through the the resistance factor 5 into the nominal tensile stress of the bolt, okay, and the gross area, and that is worked out to be 46 kilonewton, which is okay. Tensile resistance is much greater than the tension, applied tension, that's a 4 kilonewton. And please remember that whenever we perform any manual calculations, we don't have any kind of tensions, but this being Idea Statica being a finite element analysis program, it takes care of the outer plane deformations of the plate, which obviously will introduce some kind of a tension depending upon the plate deformation, right? So here, so please look here. So we don't have any problem. We have got a tensile strength of a single bolt of 46 kilonewton, which is very much higher than 4 kilonewton. So please look here. These are the very important thing. These are the F and T is the nominal tensile stress which has to be taken from the AIC 36016 table J 3.2, and this is nothing but the gross area of the bolt, which we assumed as approximately 16 mm, and we have got the resistance factor 0.75. Substituting this, we obtain the tensile strength of our normal bolt. Now Idea Statica also has provided us the shear resistance of the bolt, and that is again calculated using the standard formula available in AIC 36016, and here we have to refer J 3.1. And here what is very important is that in this expression F and V, it is nothing but it's a nominal shear stress to be used for the bolt capacity calculation, and this has to be taken from table J 3.2, right? And the gross area is already given, and the resistance factor is also available to us, that's 0.75. And what we find is that we have a shear capacity per bolt, okay, that is I'm talking about the bolt that is connecting the angle with the beam web and the column flange, 27.6 capacity, which is very much higher than 9.3 kilonewton. So we don't have much problem. And then coming to in addition to the shear, it also performs the bearing resistance check, as you can see here. That is again done using the J 3.6. Okay, and we find that the capacity as far as the bearing is concerned is very high. Okay, so we don't have much problem, right? So this is one very important calculation to be checked by the engineers before finalizing the connection. Okay, so this is all regarding the check for what we call as the normal bolts. Now let me take you to the slip critical bolts. Obviously these are the bolts we have employed in connecting the top and the flange plates to the what we call as the beam flange. Look here, so we find that just arrange the utility ratios. We find that we have 98.8 ratios and all. Let us see what is the, so we please look into here. We have got for this, let us consider the B15. Just select it. Yes, look here, this is your B15. Okay, that is the bolt somewhere here. There's a bolt, okay, that is near in the connection near the column flange. So the 15, and you can see that is subjected to a nominal tensile loading of 4.6 and the critical being 67.4 kilonewton. And please remember one very important thing: the moment which is converted into a push and pull, it will finally get transformed into the shear loading on the bolt shanks. Now the slip critical resistance is also given 68.2, and the utility ratio is given in tension as well as in a shear. In shear it is 98.8. So let us quickly see how the calculations have been arrived. So as usual, okay, we know that the tension resistance is done using the standard formula available, which we have just now discussed. So no discussion is required. But this is a very important thing. That's a slip resistance check, which is done using AISC 360 J3.8. And look here, this expression is very important, and we need to have a good understanding of the various parameters of this expression. Here you can see that the design resistance is obtained as phi into KSC into mu into ds into hf into tb into ns. So this is calculated to be 68.2. So from the perspective of the applied pretension, the shear resistance or the slip resistance is 68.2, and this is obviously is greater than 67.4. That is less than. That's why they are almost near to each other. That's why we get a ratio to the tune of 98.8. Now here the parameters are very important, because here we find that mu is the important parameter. That's a 0.30. This obviously depends upon the type of the surfaces, whether it is a painted one, uncoated surface, etc. Normally we have the two values of mu that is being recommended, that's a 0.3 and 0.35, and then there is a d factor, du factor, that's 1.13, and this basically is a factor that it takes care of, okay, the ratio of the mean installed bolt pretension to the specified minimum bolt pretension. So please remember that depending upon the bolt diameter, AISC specifies the minimum, okay, bolt pretension to be applied. So now depending upon the techniques used, we expect some kind of a variation, okay, and this d factor takes care of that variation, and HF is the factor for fillers. Now the problem is, depending upon, in many of the cases, we may have to introduce some fillers between the plates. In this case, as you can see, that we did not use any fillers between the plates. So here HF, the factor for the filler, is taken as 1, and TB is, this is a very important thing, this is a 205.1 kilonewton. This is the minimum preloading force to be applied to the given M24 bolt, okay, and this has to be taken from the AISC standard table, okay, which is again chapter J, right? And here is another important thing, that's a K factor, KSC, that's a 0.98. And now you may ask me, what exactly? This is a factor for combined tension shear. Now the problem is that, so we know that actually, as far as the slip critical bolts are concerned, their shear resistance is derived out of a friction, and which again depends upon the resistance depends upon the applied preloading, pre-tension applied to the bolt. Now, if slip critical bolts are subjected to tension, what happens is that these bolts tension will be, the applied tension will be relaxed, and accordingly what happens is that the slip of friction that is available to us, or the capacity of the slip critical bolt, reduces in shear when they are also subjected to additional tension loading, because any tension applied on externally applied on the slip critical bolt obviously will reduce its shear resistance. So the K factor takes care of the presence of any applied tension in addition to the shear, okay, and this has to be calculated using this expression, and phi is a resistance factor for slip resistance connection, that is taken as 1, okay. So this is how the connection checks are being done, and in the welds we don't have much problem, okay. So, and here it is a, yes, it's a butt weld, did not provide us any kind of a result directly here. So that's all about this tutorial, and my sincere request is that before doing any tutorial with your own hands, please ensure that your basics are very much in place and you are conversant with the various code provisions. Okay, read the code provisions first, understand the material specifications, understand the basis how the slip critical bolts work, okay, then only get into the Idea Statica, because just modeling a joint and then getting the results is not the job. That kind of job can be done even by a non-technical or a non-engineering person, but an engineer has to check each and every component, ensure that yes, the checks have been done as per the code specifications, and that there are no mistakes, okay, provided either in terms of the geometry or in terms of the material specifications. So this can be easily catch hold of when we review the results, okay. So thanks a lot. So please subscribe to the channel, because we are going to add in future, because now the problem is that I have to get time also many more interesting tutorials. So please also give a message to your friends also to subscribe the channel, because you can start learning a lot of things from these tutorials, and in future, obviously in a month or a 2 months time, we are getting into the modeling of the seismically qualified joints as well. And meanwhile, whenever I get time, I will see that I will start introducing some simple tutorials on the manufacturing operations, because the manufacturing operations you have to be very much thorough, because and it forms actually is a major procedure in the development of the model as well. So that's all. Thanks a lot and have a nice day.